Welcome to G Fun Facts Online. Our Sun, the star at the center of our solar system, is a giver of life, a celestial engine powering our planet. But this familiar star has a violent, tempestuous side. It can unleash torrents of energy that, when they strike Earth, trigger spectacular auroral displays, but also threaten to cripple the technological backbone of our modern world. These events are called geomagnetic storms, and today we're diving into the intricate science of how we predict these cosmic squalls to protect our civilization. For most of history, the first clues of the Sun's connection to Earth were a mystery. In 1806, explorer Alexander von Humboldt noticed his compass behaving erratically during an aurora. But the true wake-up call came on September 1, 1859. An English amateur astronomer, Richard Carrington, was sketching sunspots when he saw two patches of intensely bright white light erupt from the Sun's surface. Just over 17 hours later, the fastest coronal mass ejection ever recorded slammed into Earth's magnetic field. This became known as the Carrington event, the most powerful geomagnetic storm in recorded history. The effects were stunning. Telegraph systems across Europe and North America failed. Sparks flew from the equipment, shocking operators and setting telegraph paper on fire. Incredibly, some operators could send messages even after disconnecting their batteries, powered solely by the intense electrical currents induced in the wires by the storm. The auroras, normally confined to the poles, were seen as far south as Cuba. The light was so brilliant that people in the northeastern United States could read newspapers by it at night. In 1859, our technology was in its infancy. A storm of that magnitude today would be a global catastrophe, with potential for trillions of dollars in damage and widespread, long-lasting blackouts. Other storms have served as stark reminders. In May 1921, a major storm caused widespread disruption and even triggered fires at railroad signal stations in New York. But the modern wake-up call was the storm of March 13, 1989. Following a massive solar flare, a severe geomagnetic storm caused the entire Hydro-Quebec power grid in Canada to collapse in less than 2 minutes. 6 million people were plunged into darkness for 9 hours. The storm also affected satellites, radio communications, and even damaged a transformer at a nuclear power plant in New Jersey. These events have made one thing clear: we need to be able to forecast these solar tantrums. So, how does this all work? It's a cosmic dance between the Sun and the Earth. The Sun isn't a static ball of fire. It's a magnetically active star. It has an activity cycle that waxes and wanes roughly every 11 years, which we track by counting sunspots. These sunspots are cooler, darker areas caused by intense, tangled magnetic fields poking through the Sun's surface. It's from these magnetically active regions that the main drivers of geomagnetic storms are born: solar flares and coronal mass ejections, or CMEs. A solar flare is an intense burst of radiation, light and energy that travels at the speed of light, reaching Earth in about 8 minutes. The X-rays from a powerful flare can ionize the upper layers of our atmosphere, causing radio blackouts for high-frequency communications used by airlines and amateur radio operators. But the real heavy hitters are the coronal mass ejections, or CMEs. These are distinct from flares, though often associated with them. A CME is a massive eruption of plasma and magnetic field from the Sun's outer atmosphere, the corona. Think of it as a billion-ton cloud of magnetized gas hurled into space. When this cloud is aimed at Earth, it's the primary cause of major geomagnetic storms. Unlike the radiation from a flare, a CME is a physical cloud of matter. It travels much more slowly, taking anywhere from 18 hours to several days to cross the 93 million miles to our planet. This travel time is the crucial window that makes forecasting their impact possible. As this material streams away from the Sun, it forms part of the solar wind, a constant flow of charged particles, mostly electrons and protons, that carries the Sun's magnetic field with it. We call this the interplanetary magnetic field. or IMF. Luckily, Earth has a shield. Our planet's own magnetic field, the magnetosphere, creates a protective bubble that deflects most of the solar wind. A geomagnetic storm is essentially a major disturbance of this magnetosphere, caused when a CME slams into it, compressing and distorting our magnetic shield. The key to a truly powerful storm lies in a process called magnetic reconnection. Our magnetosphere's magnetic field generally points northward at the front that faces the Sun. If the magnetic field carried within the incoming CME, the IMF, has a strong component that points southward opposite to ours, things get interesting. Imagine two sets of magnetic field lines pointing in opposite directions, being pushed together. They can break and reconnect, creating a new configuration and releasing a tremendous amount of stored energy. This process is like a key unlocking a door, opening a direct channel for energy and charged particles from the solar wind to pour into our magnetosphere. This sudden injection of energy drives powerful electric currents in our upper atmosphere, creating the beautiful auroras. But these same currents can induce damaging currents in our ground-based infrastructure, like power grids and pipelines. Given the potential for destruction, an international fleet of spacecraft and a network of ground-based observatories act as our sentinels, watching the Sun and the space between us. To predict a storm, you first have to see it coming. Several spacecraft are dedicated to this task. The Solar and Heliospheric Observatory, or SOHO, a joint NASA and European Space Agency mission launched in 1995, has been a workhorse. It's positioned at the L1 Lagrange point, a gravitationally stable spot about 1 million miles from Earth towards the Sun. SOHO uses instruments called coronagraphs to block the Sun's bright face, allowing it to see the much fainter corona and spot CMEs as they erupt. To get a three-dimensional view, NASA launched the twin stereo spacecraft in 2006. One orbits ahead of Earth and one trails behind, giving us different perspectives. This allows scientists to better track a CME's trajectory and determine if it's heading for Earth. Then there's the Solar Dynamics Observatory, or SDO, launched in 2010. SDO provides incredibly high-definition images of the Sun in multiple wavelengths, letting us watch the complex dance of magnetic fields that leads to these eruptions in the first place. Once a CME is on its way, the next critical step is to measure its properties before it hits us. This is the job of spacecraft at that same L1 point, which act as our space weather buoys. The DSCOVR satellite, the Deep Space Climate Observatory, is our primary source of real-time solar wind data. It measures the speed, density, and temperature of the approaching solar wind. Most importantly, it measures the strength and direction of the interplanetary magnetic field. When DSCOVR detects a high-speed cloud of plasma with a strong, sustained, southward-pointing magnetic field, it's a red alert. This detection gives forecasters a crucial 15 to 60-minute lead time before the storm's main phase impacts Earth. Finally, other satellites and ground instruments monitor the effects here at home. The GOES series of satellites in geostationary orbit continuously monitor the near-Earth space environment, while a global network of ground-based magnetometers directly measures fluctuations in Earth's magnetic field, giving us a real-time gauge of a storm's intensity. All this data flows into space weather prediction centers around the world, most notably NOAA's Space Weather Prediction Center, or SWPC, in the United States. Here, human forecasters and powerful computer models work together to turn these observations into actionable forecasts. Predicting a CME's impact is incredibly complex. Forecasters use sophisticated physics-based models, particularly magnetohydrodynamic, or MHD models. MHD treats the solar wind plasma as a single conducting fluid, allowing scientists to simulate its flow through space and its interaction with Earth's magnetic field. These models can provide detailed predictions of the state of the magnetosphere and the potential for damaging induced currents on the ground. They also use empirical models, which rely on historical data and statistical relationships to make quick forecasts. Despite the increasing power of these models, human expertise remains essential. Forecasters analyze the data, interpret the model outputs, and issue alerts, watches, and warnings to stakeholders like power companies, satellite operators, and airlines. One of the biggest challenges remains the limited lead time. While we can see a CME leave the Sun days in advance, accurately predicting its exact arrival time, and crucially, the orientation of its magnetic field is still very difficult. That 15 to 60-minute warning from L1 is vital for immediate actions, but the Holy Grail is a lead time of hours or even days. This is where the future of forecasting is headed, driven by artificial intelligence and new technologies. AI and machine learning are perfectly suited to finding subtle patterns in the vast datasets from our solar observatories. AI algorithms can analyze years of solar imagery to identify the characteristics of active regions that are more likely to produce major, Earth-directed CMEs. By training on historical data, machine learning models have already shown they can predict the arrival time and intensity of storms with greater accuracy than some traditional methods. This could dramatically improve the precision and timeliness of our warnings. New missions are also on the horizon. The European Space Agency's Vigil mission, planned for the mid-2020s, will be positioned at the L5 Lagrange point. This unique vantage point, trailing behind Earth in its orbit, will allow it to see the side of the Sun before it rotates to face us. This will give us an earlier view of potentially hazardous active regions and provide several days of advance warning for certain types of events, like high-speed solar wind streams. The stakes for improving these forecasts are incredibly high. Our modern way of life is deeply vulnerable to the Sun's whims. The primary threat is to our power grids. Geomagnetically induced currents, or GICs, are low-frequency DC currents that can flow into high-voltage transformers, causing them to overheat and fail. A widespread blackout from a Carrington-scale event could cascade across interconnected systems, with estimated economic losses in the trillions of dollars. Satellites are also at risk. Increased atmospheric drag during a storm can cause satellites in low Earth orbit to lose altitude. In February 2022, a moderate storm was responsible for the loss of 38 newly launched Starlink satellites. The energetic particles from a storm can also damage sensitive electronics, disrupting satellite operations for communications and navigation systems like GPS. This affects everything from aviation to precision agriculture. Airlines are particularly sensitive. High-frequency radio, used for communication on polar routes, can be blacked out by solar flares. During major storms, these flights must be rerouted to lower latitudes to maintain communication and protect passengers and crew from increased radiation exposure. But with timely forecasts, we can prepare. Power companies can adjust grid loads and postpone maintenance to increase resilience. Satellite operators can put their spacecraft into a protective safe mode. Airlines can reroute flights. A 2020 study estimated that NOAA's space weather forecasts helped the U.S. electric power industry alone avoid losses ranging from $111 million to $27 billion per storm, proving the immense value of this work. We live in the outer atmosphere of a variable, magnetically active star. The same forces that paint our skies with the ethereal beauty of the aurora can cripple the technologies that define our modern world. We cannot stop the sun from unleashing its fury, but we are no longer its unsuspecting victims. Through vigilant observation, sophisticated modeling, and international cooperation, we have learned to read the signs and anticipate the blows. The journey is far from over. It is a continuous effort of scientific discovery and technological innovation. From the first puzzled observations of a wavering compass needle to the AI-driven forecasts of tomorrow, our ability to understand and predict geomagnetic storms is a testament to human ingenuity. As we continue to refine our methods, we strengthen our resilience, ensuring that our society can weather the inevitable storms that our magnificent, volatile star sends our way. Thank you for listening to G Fun Facts Online.